Okay, now I hope you got some flavor of this light matter connection, right. Now you can also, instead of doing this perturbation theory, which can get quite involved in terms of analytic work, you can develop some feeling for this process using a numerical simulation, but then you can do numerical solutions for very simple systems. So therefore, quickly, of course, you can do some large systems, of course, but that becomes a research gate problem. But here what you can do is, for the purpose of the lecture, I have taken a very simple system. This is a one dimensional Hamiltonian for an atom, okay, for atom. So this is some model potential in one dimension, which gives you the same ground state energy as a real hydrogen atom, right. It's called a soft core Coulomb potential, and this is your H laser. Now if you solve this numerically, okay, I'll show some results as to how the numerical simulation can be done. But first, because I have this field strength, let's develop some feeling for these field strengths, okay, that will get into the numerical values. Okay. So when I say a particular field is weak or strong, I need to compare it against something. Okay. What is that I need to compare it against? So if I have an atom that's a proton and then there is an electron that's bound to this proton, there is actually an electric field that is binding the electron and proton. Now if I shine a laser on it, it has a certain field strength. Now how does this electric field of this incident electromagnetic radiation compare with the Coulomb potential that is binding the electron to the proton? That is what tells us whether the field is strong or weak. Okay, I need some relative measure. So if you now compute what is the field strength of a typical Coulomb potential, right, this is a classical estimate. So what I am doing is the field that the electron sees is E by 4 pi epsilon naught r square, and for r square I take the Bohr radius, and what you get out of this is 1 atomic unit in so called atomic units. What one does in atomic units is to take E is equal to 1, 1 by 4 pi epsilon naught is 1, C is 1, and A naught, which is the Bohr radius, is also 1. So you make a lot of things 1 to make the equations look simpler. It's essentially a unit system. It's like instead of measuring in terms of meters, I say I'll measure it in terms of the units of the Bohr radius and so on. Okay. So there is an equivalent system that's used in atomic physics. Now 1 atomic unit of field strength in SI units corresponds to the following. Okay, that's 5 times 10 to the 11 volt per meter. Okay, just to get some feeling for numbers. Now if I have a monochromatic wave and I compute the average intensity with this particular field strength, I get 3 times 10 to the 16 watt per centimeter square. Okay. Let's keep this as a reference, assume that I have calculated this correctly. So 1 atomic unit, that's the thing that's binding the electron with proton, corresponds to this particular field strength, and if I have a monochromatic field with the same field strength, it corresponds to 3 times 10 to the 6 watt per centimeter square of average intensity. Now let's scale this down. Yeah. So 1 corresponds to 3 times 10 to the 16. Now if I have 0.1 field, because I have an E square dependence, the intensity drops by 100. Okay. So I have computed for a different field strength. Now what do I mean by weak? Maybe it's something like 0.01% of the thing that's binding this atom and putting the atom together, that might be considered weak. Maybe it's like 0.001 of it or 0.005 of it or something. Now let's take weak fields and do a numerical simulation for this first part of this lecture. So how do I do this numerical simulation? I want to solve this time dependent Schrodinger equation. What one does is, this is a one dimensional problem, so therefore let us say this is psi, this is the origin, and I have my x axis going from minus infinity to plus infinity, that's my x axis. You discretize, create a grid on this x axis, and then express your wave function at each of these grid points as some value psi I. So what you are doing is, you are expressing psi at xi at each of these grid points is psi I. So that's how you discretize this wave function. Now once you discretize this wave function, you can set up the matrix representation of the Hamiltonian operator. So this is simple, so let me write down. So if I want to compute h, it has the kinetic energy which is minus half del square, that is the simple kinetic energy without the h bar which or the m, because we have set all of them to 1 in atomic units. So and also it is just a one dimensional problem, so this becomes in one dimension it is minus half d square by dx square. Okay. So this, what is d by dx? An approximate formula for d by dx is going to be or if I want to, where is this? I want to compute what is the derivative of psi at some ith point. If I want to compute this, you can use a simple formula which is psi I plus 1 minus psi I by delta x. Okay, that is an approximate formula for the derivative where this grid spacing is delta x. Now if I want the second derivative, I can use the first derivative twice, and then I can compute psi I second derivative as psi I plus 1, it gives you minus 2 psi I plus psi I minus 1 by delta x square. Okay. Now this is your kinetic energy with a half, right. I want to evaluate the second derivative of the wave function. Now this in a matrix representation becomes a tridiagonal matrix. So because you have, if I evaluate the derivative at the ith point, it depends on the value of the function at the ith point, and it also depends on the value of the function at one point before and one point after. So this is the ith point, this is the I minus 1 point, and this is the I plus 1 point. So matrix representation of this operator would mean I have something like psi 1, psi 2 and so on, that is the value of the wave function, and the matrix representation is a tridiagonal matrix. Okay. On the diagonal you have minus 2 by del x square, and on the off diagonals you have 1 by del x square. Okay. So I can evaluate this psi I double prime using this matrix representation of the kinetic energy operator. Now in the same way you can also get the matrix representation of the potential energy operator, which is just evaluating the function at the grid points. Okay. So now you set up this matrix, so you have then a set of coupled ordinary differential equations, you solve that, you get psi of t, and once you get psi of t, you can then evaluate this expectation value and compute the Fourier transform of this expectation value. So these are the steps, right. You discretize on a grid, you find out such a matrix representation of the operator. Once you have this, right, I differentiate this psi, but psi is now represented as grid points on grid points. So I get a set of coupled ordinary differential equations that can be solved. Once I solve it, I have actually psi as a function of time, and that psi as a function of time can be used to compute this expectation value, r is a function of time. And if I want to know what are the Fourier components in this polarization, what do I have to do? I do a Fourier transform, right. The Fourier transform will tell me what are all the frequencies in this time varying function. Now I have some results for a few low fields here, small. So this is an example for field is 0.005. Okay. Let me explain this. So on the left hand side what you have is plotted is the density of the wave function. This is my x coordinate and this is my time coordinate. I take a very long pulse, okay, and what I am plotting is psi square as a function of time. So how do I understand this? If I start off here where the laser pulse has not yet arrived, so that means the E field is 0, and I plot this, so this is a color coding, so this yellow would correspond to the maximum value and blue would correspond to the minimum value. So if I now plot a slice of this at this starting t value, it would look like the following. I plot x versus psi square. You see the maximum is at the origin, so therefore it would look something like this, okay, a well localized function. Now you see what happens to this as a function of time. You see that it starts oscillating, right. I hope you see this little oscillations, right. Maybe I will try to draw this. Right, you see, no, it's not yet right. Okay, you see this little oscillation. That means your wave function is kind of spreading over and coming back, spreading over and coming back, and that's essentially the generation of polarization. Okay, so that means your electron cloud is spreading over and coming back, and it's following this electric field. Now, if you compute the expectation value of R, you see that it also oscillates. Right, this is the expectation value of R. It also oscillates, and it follows essentially the oscillation of the field. However, if you take the Fourier transform of this, you see that I have normalized it omega with respect to omega naught, the driving field, and that's the intensity at each frequency, and you see that you still have a large peak at the first harmonic. It's not harmonic, but it's at the driving field, but you also start seeing that there is a certain intensity at 3 omega, there is a certain intensity at 5 omega, and so on. Right. So that's how harmonics are generated. And one more important observation is, if I look at the relative strength of this original driving field versus the harmonic, the third harmonic, you see that it's about a factor, I don't know, 1 by 1000, right. So let's say this is approximately 1, sorry, no, that's actually 10 versus 10 to the minus 3, so that's 10 to the 4. So I have a relative intensity difference of 10 to the 4. Now if I look at the next one, this is a little bit noisy, but it also falls off by maybe a factor 100. Okay. So that's why these harmonics are not very easy to see, right. Although in when I wrote down the polarization for the Maxwell's equation, I wrote P is proportional to E square and so on. But how intense is this harmonic is given by that coefficient. And from where do we get the coefficient? It comes from the material response. In the perturbation theory, although you see the frequencies and the dependence on the electric field and the intensity, you don't actually calculate all the matrix elements. So it's also possible to compute all those matrix elements, but a simpler way is to just demonstrate it through this one-dimensional simulation, and you see that that prefactor is quite small, and you see that it's not easy to get intense harmonics. Okay, and that's why it's a challenging thing to generate harmonics.
Any physical reason why the intensity decreases?
Yeah, basically if you look at the physical interpretation from the transitions perspective, you see that what does quantum mechanics say? I have a certain probability for a certain transition to occur, correct? It's a probability, and it's going to be less than 1. Now if I'm going to have 3 transitions instead of a 1 transition, that means I have some probability which is less than 1 multiplied by another number less than 1 times another number less than 1. So it's going to keep reducing. The more the transitions, it's going to keep reducing.
Can it be interpreted as 3 photons being absorbed by 1 atom? And then
yeah, you can interpret it that way. But here it's a third harmonic, so you have 3 photons and then 1 photon coming out. Yes.
What are the specific parameters that have been changed to get peaks on your 3 omega and 5 omega?
Basically, you take a long pulse, you will get peaks. If you take a short pulse, you see a blob. Right? It's essentially Fourier transform. So if I have many oscillations in my time signal, I would see peaks. Right? If I have a single cycle pulse, there is actually no periodicity, right? But it's quasi-periodic, so you can do a Fourier transform, and then you still get a blob in the Fourier transform. Right? So this exactly harmonics would remind you of Fourier series, right? Which means I have infinite periodicity. Yes, please. Yes.
The number of cycles in the pulse also determines the amplitude of the Fourier transform. Higher the number of cycles.
No, the peak will be the same, but the contrast will increase. So if I have even more cycles, then you will see that this thing will even come down, right? That contrast, it will become more and more delta-like pulse, but the height will always remain same if you normalize it correctly.
Oh yeah, after normalization.
Yeah.
So these are relative intensities and not arbitrary.
Right, these are arbitrary. But what is more important is the height of this with respect to this will always remain the same. I may have an overall factor, but the ratio of this first peak to second peak will always remain the same.
How,
Yes.
How would you tweak the input pulse so as to get a specific peaks and specific harmonics?
No, you don't need to tweak much. So it's just to do with the field strength. So let's say I have a long pulse. You need to have in a numerical solution some start and stop, because you cannot have an infinite pulse. and it's just the driving frequency and the amplitude, right? So now let's say I increase the field strength, right? I have taken a very small field strength. So this 0.005 is with respect to that one atomic unit which is keeping the atom intact, right? So this is a small fraction of that field. Now let's say I increase the field strength, so I make it twice of that, and now let's see what happens. You see that I have the same behavior, right? I see oscillations in this density. Yes, yes. This is okay. Yes. So you still see this same kind of oscillations in the density. You have a very similar looking expectation value of R, but the details are in the Fourier transform, right? When you look at the Fourier transform, again I get a peak at 1 omega, this is 3 omega, that's 5 omega, 7 omega, and so on. Okay. The higher the intensity, it now starts becoming a little bit more probable to have those higher order terms and start generating higher frequencies. But then you see that they still keep dropping by at least an order of magnitude, right? So that's with the weak fields. Now, yes.
Is there any reason why the Fourier spectra showing only the odd harmonics?
Yes, that's on the next slide. Yes, very good observation. So you see that you only have odd harmonics in this particular problem. Now, why is it the case? This is something to do with the symmetry of the system. Okay, a very simple answer would be the following. So if I take some atom, let's go back to this picture. I have some electron that's getting distorted, the electron cloud. Now, if I change the direction, what should our physical intuition say? If with the electric field in this direction, I have a distortion of this form, whereas if I swap the direction of the electric field, what should happen? Our intuition should say that my polarization should be with the opposite sign, correct? But then if I have my polarization to be proportional to the field's strength, but e to the power 2n, okay, E becomes minus E. So E becomes minus E. This intuition tells me that P should become minus P. But if I have P to be proportional to e to the power some 2n, where n is an integer, the even power, so that would correspond to the second order, fourth order, sixth order. Because I have an e to the power 2n, it tells me that the minus sign is cancelled out. Let's say I have e square. Then it tells me even if I swap the sign, P will still be proportional to e, but not to the minus e. Now this can only happen if it is 0, right? That's why if I have an inversion symmetric system like a simple spherical atom, then all the even harmonics disappear for symmetry reasons. You cannot have those, what do you say, those even harmonics. Okay. Another way to also understand this is if I have a driving field which is like this, right? Now this half of the cycle does exactly same as this other half of the cycle. And if there is nothing to break this symmetry, the system has inversion symmetry, this whatever this does is same as whatever this does. So I have the same process exactly repeating, not at period t, which corresponds to the time period of this driving laser, but I have exactly the same process happening at t naught by 2. So it's half of the frequency, which would then correspond to the fact that I cannot have even harmonics. Okay, so you can understand in these two different ways, but this is for now a simple way to do. So the only way this condition can be satisfied if the polarization due to these even order terms go to 0, and that's what you also see in the simulation.
But is that possible to put in the simulation? Like usually in experimental wise, you have the second half generation or fourth half generation.
Right. If you take a system which is not symmetric, then you start getting even harmonics.
In the simulation thing, you just put a Schrodinger, you just put a hydrogen potential with a small bit of potential V.
Yeah, all that can be done. That's what I'm saying. If you make your potential which is not symmetric, then you see these even harmonics. Yes, all that can be done. Then we basically, in terms of the experimental error, considered 0. Right?
The intensity will still be low for all these even harmonics.
Yes, they'll be much lower than, basically it's been noise. I won't say it is, if you have a very clean experiment, you cannot see any even harmonics. It just comes from symmetry, right? It's a very, let's say a very fundamental thing. You need to have something in your system that breaks the symmetry.
Generally, for a system with only one polarization, right? Why are we subdividing polarizations as an expansion in P1, P2, P3?
Yes, so that just makes our analysis easier. So let us say historically, you see, if I want to generate 3 harmonics, let's go back. This is a case where I could generate basically 2 harmonics, right? This is even much smaller. What is the intensity you have? Let's go back. What is 0.005? That's 9 times 10 to the 11 watt per centimeter. So when lasers technology gets advanced and you start generating more and more intense pulses, right? At some point, people are doing experiments with such intensities, which are 10 to the 12 watt per centimeter square. So therefore, you do not really need to think about all kinds of terms in the series, and always having an expansion truncating after 1 or 2 terms make your calculations much easier, right, and gives you insight into the problem. So therefore, you truncate it after 1 or 2. Now we are in a regime where you can generate pulses on this scale, right, and therefore we talk about different regimes, right? And that's the reason why you had a conventional nonlinear optics subfield which expanded the polarization in these terms, and it worked out for that regime. Okay, so that's basically like the first lecture that I wanted to give. So the key takeaways for this is the following. So if you can understand how systems generate radiation, it's through a time varying polarization, or there will be other systems where you have time varying charges, currents, magnetization. But here in this particular example, we are interested, it's time varying polarization. Now for weak fields, you can have a certain perturbative expansion for this polarization. We looked a little bit more in detail as to what is the atom doing in the presence of the field. We computed the wave function, right, and what does this wave function tell us about polarization through the expectation value of the dipole moment operator, and we saw how the polarization oscillates with respect to time. We saw P1 oscillates with at the same frequency as the driver, P2 oscillates at twice the frequency. You see the linear dependence with the field, you see the quadratic dependence with the field. And then I showed you some simulation with the time dependent Schrodinger equation simulations with a one-dimensional solution, and you see how exactly this can be done, that you discretize the wave function, you set up the matrix elements, you set up coupled order differential equation, solve it, and then you get the expectation value of the dipole moment, do the Fourier transform, and then you see how do you get the harmonics and how does the intensity of the harmonics go down. So that's the summary. There is another very important aspect to this kind of nonlinear phenomena. Just like that energy matching resonance condition was there in the perturbative expansion, you also need a certain momentum matching because you have momentum conservation as well, and that gives to what is a condition called phase matching, which is not covered in this particular lecture. That will be for a future lecture. Okay, so that's all for today. You have any questions?